In this class, let us study about continuous functions. Continuous functions are functions whose graph is a single unbroken curve. That means there are no jumps, no breaks or no gaps in the graph. Now look at the first picture. That is exactly what you will see here. If you name this point, say P, and if you name this point Q, you will see that from P to Q, or in other words, in the interval PQ, you see that fx is an unbroken curve. So it is just continuous. So we say fx is continuous in the interval PQ. But notice we do not have any information what happens before P or what happens after Q. But we do know that from P to Q it is continuous. It is unbroken. Now look at the other three pictures. You will notice a same thing. You will notice the graph of this function fx. It is going like this, but when it passes through A, it experiences a discontinuity. So we call A a point of discontinuity, and we say that the function fx is not continuous at the point A. But if you notice these three pictures, you will see different types of discontinuities. In this picture, if you see, in this graph, you see the left side of A and the right side of A are still joined. Right? So this is what we call a removable discontinuity. But at the same time, look here, look at where A is. Here is your A. In this place, here is your A. So if you look at A, the left side of A is here and the right side of A has experienced a jump. So we call this the jump discontinuity. Now if you look at the third picture, at A, you will see that both the left side and the right side are tending towards infinity. So we call this the infinite discontinuity. We will discuss these discontinuities at a later period. Let us not meander off from our main topic, which is continuous functions. Now, coming back to continuous functions, do you think it is a feasible solution what we just now discussed, to draw a graph and to see if it is not broken? So do you think it is a feasible solution? Every time somebody asks you, is this function continuous, are you going to take a paper and a pencil and start graphing from minus infinity to infinity? Of course it is not practical. We need a more easier solution. That is where the limits step in. So with the use of limits, with just 3 simple steps, we can see whether a function is continuous at a particular point. If you are given a function fx at a certain point A, using 3 steps, we can check if it is continuous, or while passing through A, fx breaks. We can check that. What are the 3 conditions? The first condition is that f of A must be defined. The second condition is that the limit of f as x approaches A must exist. And the third condition is that these two must be equal. Now, for each of the conditions, we will take examples and we will see counter examples and we will discuss them. And then when we discuss the counter examples, when we discuss the places where this does not hold, this condition does not hold, you will see each one of these discontinuities. You will see when the condition does not hold, we will then discuss each of this. Now we go on to the first condition. What is the first condition? F of A must be defined. What does that mean? It means 2 things. If you have a function f of x and you have a point A, then f of A must be real, it must be finite. It must satisfy these 2 conditions. Now let us see some examples. Some examples where any point from the real number you take, it will exist. The function will be real, the function will be finite. So now we go on to examples and counter examples. To start with examples, the first example that should come to your mind is polynomial. Polynomials are extremely well behaved. What are polynomials? Polynomial in x, in any variable x, is an algebraic expression in x where the powers of x are what? They must be non-negative integers. It must be non-negative and it must be an integer. Then it is called a polynomial. Polynomials exist throughout the real number system, real number line. So what happens if you take a non-negative integer? For example, take a negative integer, x raised to minus 1. Then you get what? 1 by x, or any number where x comes in the denominator. That stops being a polynomial. So that is the first counter example we are going to take. For example, take x minus 5. Then what happens if it is not an integer? For example, x raised to 1 by 2, or in other words, square root of x. That is the second example we are going to take. If you have a square root of x, it stops being a polynomial. So that is our second example. So with these two examples, we will see what happens and at which point fa stops existing. So look at this function. Its domain, whatever number, whatever real number you put, the answer will be finite. The answer will be real except for what number? 5. You cannot have the point 5. Why? What happens if you put the point 5? It becomes 1 by 0, which means it tends to infinity, which means it stops being finite. So for this function, if I call this f of x, f of 5 does not exist because it is not finite. Now consider the second f of x. For any real number from 4 to infinity, see, I have put the closed interval, which means 4 is also included. 4 minus 4 is also 5. You get 0, right? That is fine. Any number from 4 to infinity, we are fine. But what can't we have? We cannot have any number from minus infinity to 4 this way. Why is that? Take a smaller number, say 3. Take a number in this. Take any number less than 4 is not acceptable. What happens when you take any number less than 4? Then this whole thing becomes a negative number. And what is the square root of minus 1? It goes to I. It goes to the complex numbers realm. It stops being what? Real. So it stops being real. So that means what? If you take this function f of x and take any number less than 4, any number such that inside the square root you will get a negative number, that number, it stops existing. So f of x, randomly I will take 2. F of 2 does not exist. Why? Because it stops being real. It becomes a complex number. So for all of these numbers, f of x will not exist. Another function which exists for the whole of the real numbers, sin x and cos x. What is the sine function? It takes any angle on this earth. Whatever angle you can think of, however steep, however narrow, it takes that angle and maps it to an interval from -1 to 1. So whatever your x is, sine of x will always be finite. It will always be real. Same with cos x. Whatever your x is, your cos x will always exist. Your cos x will always be finite, always be real. But then, what about tan x? Tan x is sin x by cos x, right? So once you have a denominator, you have a problem. Your denominator cannot be 0. If your denominator is 0, that means it is going to tend towards infinity. That means it will stop being finite. We cannot have that. So we have to remove the numbers, remove the angles for which cos x is equal to 0. So what are those angles? It is 2n plus 1 pi by 2. So if your function is a tan x, then for these angles, f of x, f of a does not exist. That means it will exist only for those angles from which this is removed. 2n plus 1 is removed. Remove this, then for the rest, f of a will exist. Now, when you say 2n plus 1 pi by 2, what does it mean? Don't get worried when you see this. All it means is that we are dealing with only the odd multiples of odd multiples of pi by 2. For example, see, if you put 0, you will get pi by 2. If you put minus 1, you will get what? You will get minus pi by 2. If you put plus 1, you will get 3 pi by 2. Only odd multiples. Why are we stressing on the only odd multiples thing? Because what happens if it is a even multiple? Then it becomes 2 pi. Then sine 2 pi by cos 2 pi is actually equal to what? It will be equal to 0 by 1. Cos 2 pi is 1. So 0 by 1 is 0, which is fine. 0 is finite. 0 is real. So we cannot have this. The whole situation changes. That is why we are stressing on the odd multiple part. So here we have seen what does it require for f of a to exist. Now, before I go to the second condition, let me ask you one thing. If your f of x is in the form of a rational number whose denominator is say x minus 5, and you are asked, does f of a exist if a is 5? Does this exist? And if a is 0 in this function for this particular fx, does f of 0 exist? We're going to put 5 here and say 5 minus 5. So 1 by 0 tends to infinity. Again, if you put 0 here, 1 minus 1, it again the denominator becomes 0, so it tends to infinity. No, don't rush to conclusions. So just take a deep breath and see what is in the numerator. What if in the numerator you have this? What if in the numerator this is the term you have? Then what happens? X square minus 25 is what? It is x applying the a square minus b square term. What is this? It is x minus 5 into x plus 5. So this whole fx now becomes what? It is just x plus 5. So f of 5 will be what? It will just be 10. So there is no problem. It is real. It is finite. Now the same here. Here you can rationalize the denominator. You will get again a square minus b square. The square of this would be, square of 1 would be 1 and the square of this would be this. So you will get what? X and x gets cancelled and you get this. So if this is your f of x, what is your f of 0? It would be 2. So you see, it is finite, it is real. So please wait. See what comes in the numerator. You can always reduce it to something finite and real in some cases by either rationalizing the denominator or by applying the a square minus b square formula. We apply that a lot in these sort of questions. So now we come to the second part of the condition. Now we come to the second condition. What does the second condition say? What do we mean by the limit of a function f at a point A? What do we mean by that? It means the expected value of f as x approaches a. So that means when x approaches a, where does f go? Where does f go? That will be your limit. Now what is the problem with that? When x approaches a means it can approach a in two ways. What two ways? See, suppose this is a. For example, take your a is 4. When we say x moves towards 4, it can move towards 4 in two ways. It can move from the left or it can move from the right. Or in other words, it can move like 3.7, 3.8, 3.9 and then it can go towards 4, or it can come from 4.3, 4.2, 4.1 and then it can come to 4. So x can approach a in two ways. So that means what? The limit of f can also be in two ways. It can be a left hand side limit or it can be a right hand side limit. So what does the left hand side limit say? It is that value of f when x approaches a from the values less than a. What is your right hand limit? It is that value of f when x approaches a from values which are greater than a, or in other words from the right. So if these two are equal, if your left hand side limit and your right hand side limit are equal, then we say that the limit of f exists at a. Again, let us take examples where the limit exists and the places where limit does not exist. So, for example, take any polynomial, for example, 10x. Now, polynomials, as I said, they are extremely well behaved. They can be used as an example anywhere in your calculus, in most of the places actually. You can use them, they are extremely well behaved. So, take f of x is equal to 10x, it is a polynomial. Now, at a is equal to 4, what is the limit of f? That is our question. So, there you have 4, then you have two ways you can calculate the limit. What if x comes from values less than 4? What if x comes from the right side, from values which are greater than 4? Now this is 10x, fx is 10x. So put values which are less than, you can start from say 3.7. So what do you have? 3.7. So you will have 37, 38, 39. It will ultimately go to 40. But then you don't have to do that every time. Understand, that is the process that is happening. It is slowly inching towards it. But you don't have to write that every time. You can just straight away write LHS, the left hand side rule, as it approaches from values less than 4. What is fx? 10 of x, which is just limit, which is just 40. So you don't have to break your head about that small changes. But just understand this is what happens. And the same thing when it comes from the right. What will you have? Start from 4.3, then you will see 43, 42, 41, then it will go up to 40. Then again what do you have? The right hand limit also is whether it comes from your left or its right, you will still get 40. So now you can also check the first condition. What was your first condition? F of a must exist. So what is f of 4? Instead of x, put 4, 40. So you see, this actually satisfies all the conditions of continuity. What was that? F of a exists. The limit from the left side and the right side are both 40. So the second condition also satisfied. Third condition also satisfied. F of a is equal to this. So that is also satisfied. So that means what? F of x is continuous at the point a is equal to 4. That we have seen an example. We will see a counter example. Some place where f of x, the limit of f at a point a does not exist. Why? Let us see that. How does this function look like? At 0, there is a split. For all the values less than 0, what will be your fx? It is 2x plus 1. For all the values greater than 0, what will it be? It will be 2x minus 1. So what happens now? You have two different functions. Such functions are known as piecewise functions. So for different intervals, fx has different values. So now let us check the first condition also. What is the first condition? We are going to check the continuity of fx at the point x is equal to 0. So first thing you have to say, if a is equal to 0, does f of 0 exist? Is it finite? Is it real? Now look here, x greater than or equal to 0. This is for x which is strictly less than 0. So greater than or equal to 0 comes here. So what is that? 2 into 0 plus 1. So this is finite. This is real. First condition satisfied. Go to the second condition. What is the left hand limit? What is that value of f which happens when x approaches 0 from the values less than 0? So that means what? If you put 0 here, you get 1. Then what is your right hand limit? What is that value of f you get when x moves towards moves towards 0 from the values greater than 0? Then what do you have here? Here if you put 0, what do you have? 2 into 0 minus 1 is minus 1. So what do you have here? A exists. first condition is good, but the second condition, what do you have? The left hand limit and the right hand limit are not same. That means the limit does not exist. That means at the point 0, your f is not continuous. Now this is not the only type that you can expect. There is something called the indeterminate form. This is our next question. We are given a function f. We have to check if it is continuous at pi by 2. Then what is the first thing we check? Is it defined at pi by 2? When x is equal to pi by 2, f is 1. So good news, it is defined. Now all we have to do is take its left hand limit, right hand limit and show that all of it is 1. Then we can prove that it is continuous at pi by 2. So let us start finding the limits. Let us first find the left hand limit. That is when x approaches pi by 2 from the left. You see what is the problem here? If instead of x you substitute pi by 2, then what do you get? It slips into something called the indeterminate form. Cos pi by 2 is 0. Pi by 2 minus pi by 2 is 0. So you get this form, which is an indeterminate form. This is not the only one. There are others. This is also an example, and then this is an example. And once something like this happens, there is a small trick we use. What do we do? What is our main purpose here? We have to get rid of this particular limit. We want to get rid of this. So instead of this, we substitute it with another limit. How do we do that? Let me show you. Suppose the point where you have to check the continuity is a. Then for all the values less than a, instead of x, put a minus h. For all values greater than a, instead of x, put a plus h. So as x approaches a from the left, we can substitute this limit by h approaches 0. Same here. Instead of saying x approaches a from the right, we can say h approaches 0. And how does this work? What is the logic behind it? Instead of a, I will take 4 and we will see how this works. For all values less than 4, what are you going to take? Take x is equal to 4 minus h. For all values above 4, take x is equal to 4 plus h. Here h is an incredibly small amount, like 0.2, 0.1. It is very small. Then as h tends to 0, what happens? Suppose h goes from 0.4, 0.3, 0.2 to 0.1 and then it slips to 0. So as h goes towards 0, what happens to x? X is 4 minus h, right? So 4 minus 0.4. So this is what? 3.6, 3.7, 3.8, 3.9 and it slips into what? 4. So similarly, see what happens here. Here you have taken 4 plus h. So as h tends to 0, from 0.3, 0.2, 0.1, it goes to 0. It slips into 0. Then what happens to 4 plus h? You will see that that slips to 4. Or in other words, if x is equal to 4 plus h, you will see that this slips to 4. As h slips to 0, as h tends to 0, you will see x tends to 4. How is that? Just keep on counting. It is 4.3, 4.2, 4.1 and then finally 4. So that is exactly what we are going to do here. But instead of 4, what do we have? Instead of 4, we have pi by 2. We have pi by 2. And then for the left hand limit, what will we take? Instead of x, wherever you see x, instead of that, put pi by 2 minus h. Wherever you see x on the right hand side, instead of x, put pi by 2 plus h. And then what do? You can substitute this limit by h tends to 0 and you can substitute this limit by h tends to 0. So now try that. Now this will give you an answer. So now this is what happens when you substitute pi by 2 minus h for x. Wherever you see x here, substitute pi by 2 minus h. Then this is what you get. Applying cos a minus b, you get this, but cos pi by 2 is what? 0. So this whole term becomes 0. Sin pi by 2 is what? 1. Then sin h by h, as h approaches 0, it will be 1. Remember these two limit rules, both sin x by x and tan x by x. When x approaches 0, this whole thing approaches 1. So you have got your left hand limit is the same as this, so 1. Now we will find the right hand limit also. It is the same, except for wherever you see minus here, you just put a plus. That is what we do, right? So before pi by 2, we take it as pi by 2 minus h. After pi by 2, that is to the right, for the right hand limit, we take it as pi by 2 plus h. So wherever you see minus, you just have to keep on putting plus. So you get this, but then remember cos a plus b, there is a small difference in the formula. You remember it is cos a cos b minus sin a sin b. So here you get 1, but the whole of this term becomes minus sin h. And in the denominator also, you see, when you open the brackets, you get minus h. So in both of this you get minus, which gets cancelled, and it is still the same. The answer is still the same, it is 1. So what do you have? Fx is continuous at pi by 2. This is our first question. What is it given? It is given that f is continuous at 1. It is already given. So to make f continuous at 1, what should be the values of a and b? That is what we have to find out. If f is continuous at 1, what will you have? This will be real and it will be finite. The left hand limit will be equal to the right hand limit, and then we say that the limit exists at f. So we have to find all the three. What is f of 1? At x is equal to 1, the value is already given, it is 11. So these two must also be equal to 11, or in other words, we will equate it to 11. So when x approaches 1, from the values less than 1, here, see, these are the values which are less than 1. Then what happens? Substitute 1 here, you get 5a minus 2b. Now, these are the values where x is greater than 1. Then what do you have? Again, you have a and b. Here, x. Instead of x, put 1. Then you have 3a plus b. But then if it is continuous, both of this will be equal to 11. So equate it to 11. So now you have a equation. So on solving it, you will get a to be 3. And you will get b to be 2. So if a is 3 and b is 2, we can say that f is continuous at 1. Now we come to the second question. What is given? A function f of x. It is given that if f is continuous at 0, if f has to be continuous at 0, what is the value for a which will make it continuous? Again, go the same way. Look at the first thing. F of 0 is equal to what? It will be a. Now the left hand limit and the right hand limit have to be equal. Then we will say that the limit exists. This is our function. But what is 1 minus cos 4 theta? Do you remember this formula? Cos 2 theta is cos square theta minus sin square theta. But if you want to get rid of cos square theta, you want an answer only in terms of sin square theta, then what do? Apply this. Cos square theta is equal to 1 minus sin square theta. So you will get this. Now, if you want it only in terms of cos square theta, you don't want sine here, then the same thing. Instead of substituting for sine square theta, substitute for cos square theta, then you get here. And now you see the difference. Both of them will give you two different formulas for the same thing. For the same cos 2 theta, you will get two different equations. One is what? Sin square theta would be 1 minus cos 2 theta. But at the same time, cos square theta, you will get 1 plus cos 2 theta. A small difference, but then which one do we need? We need 1 minus cos 4 theta. So that will be what? 2 sin square 2x, right? So here you have 4x. Instead of 2 theta, you have 4x. So it is 2 sine square 2x by x square. Then what do you have? Remember this one? Limit of x tends to 0, sine x by x will give you 1. That is what we are trying to do. But here we have sine 2x. So that means in the denominator also we need 2x into 2x, right? But then we have 2 into 2, we need 4. We can't just multiply the denominator by 4, right? In the numerator also we have to put a 4. So here all we are doing is making it 4. So it is 2x the whole square. That is what you are getting. So you have 8 sine 2x by 2x the whole square. Now what is this? This is our fx, right? So as limit x tends to 0, what do you have? You have 8. 8 does not have an x. It is a constant term. So we can take it out. The whole square. The whole thing tends to 1. So this is your answer. So the limit of f at 0 x's and it is equal to a. So if 0 is continuous at a, then this a will be equal to 8. That is your answer. We come to 2 practice questions. Look at the first function f of x. Where do you see the break? The break is at 0. So at 0, you see that this f of x behaves like a piecewise function. It has 2 different values. One before 0, one after 0. Now, what should be the value of k if it is continuous at the point 0? So let us assume that at 0 it is continuous. Then what is f of 0? Look, where you have the strict inequality, don't go there. Here see, x is strictly greater than 0. Don't go to the strict inequality, go to here, this one. This here is less than or equal to. So that is where you will get the value of x is equal to 0. If you put x is equal to 0, you get 2k. Now find the left hand limit. Come from values which are less than 0. Where do you have here? This. And what is the function that you have? It is x squared plus 2. So then again substituting x is equal to 0, you have it as 2k. Now come from values which are greater than 0. Then you have what? The function changes. Now it is 3x plus 1. Again substituting x is equal to 0, you get what? It is 1. Now if f has to be continuous at 0, then all the 3 values must be equal. Only if these 2 are equal, we can say the second condition is satisfied. If these 2 are equal, that means what? K is equal to half. Again, you will see that the same thing, it is satisfied here. If k is equal to half, you will see that your function is continuous at the point 0. Now you have 2 points where you have to check. Both at 3 and at 5 you have to check, because at both the points you see that the fx value is changing. First stick to a is equal to 3. At 3, what is the value? Where do you have? See, here is where you have x is equal to 3. Here you have a strict inequality. X is equal to 3 is 1. Then come from values which are less than 3. Where are they? Here. Your function is 1. It is a constant function. There is no job for x here. There is no x. Whatever your x is, it is a constant function. Now come from values greater than 3. What do you have? Greater than 3, you have this. Instead of x, put 3 here. You have the answer to be 3a plus b. Now consider all of this, but for this time for what? For the number 5. So f of 5 is what? Here is where you get the equal to value. It is 7. Come from its left, the values which are less than 5. Where do you have this? Here. At that part, instead of x, put f. Now you come from values greater than 5. Then what do you have? Whenever x is greater than 5, your function is 7. So wherever you see an x, put 5. There is no x at all. There is no place we can substitute it with 5. So this is 7 itself. Now, if we want our function f of x to be continuous at 3, then all of this should be equal. 3a plus b should be equal to 1. Now, if we want our function to be continuous at 5, all of this should be equal. In particular, you should this condition should be satisfied. Only then we can say that the limit exists. Now, solve these two equations and you will get your answer. What are the two equations? 5a plus b is equal to 7. 3a plus b is equal to 1. Then subtracting these two equations, you will get 2a is equal to 6, which is a is equal to 3. If a is equal to 3, then b will be equal to what? Minus 8. So these are the two values for which your function will be continuous at both 3 and 5. Now look at this question. What should be the value of k if f is continuous at 2? You see at 2 you have a break. So let us start solving. F of 2 will be what? It is given as k. Now the limit of x tends to 2 of fx. What is this? If you substitute 2 here, what will you see? 4 square is 16. 16 minus 16, you will get a 0 in the denominator. We don't want that. Just look at it. Is there any way you can simplify it? See, lot of common terms, right? Try taking 2 raised to 2 outside. If you remember the law of exponents, a raised to m into a raised to n is equal to a raised to m plus n. So we have taken this 2 square outside. So here you have 2 raised to 2, and in the numerator what do you have? Again 4 raised to x, you can write it as 2 raised to 2 into x, right? And what is that? A raised to m the whole raised to n is equal to a raised to mn. Remember that? So instead of this, you can write here like this, 2 raised to 4. Now what form is this? Can you see? It is again you are getting the a square minus b square form. You can write it as 2 raised to x minus 2 square by 2 raised to x plus 2 square. So this whole thing gets cancelled and you are left with 4 by 2 raised to x plus 4. Just this term. And now put x is equal to 2. Then what will you see? You will see that it is your denominator is now 8. So the whole thing now becomes what? 1 by 2. So your k is 1 by 2. Now we have done so many questions finding a value for the variable so that this fx will turn out to be continuous at the point where the function experiences a split, right? So now we will take a counter example. Now we will prove that whatever your value of k is, 100, 200, 1, 3, it will never be continuous at 0. And why is that? Let us check. Suppose what is the condition to be satisfied if it has to be continuous at 0? F of 0 must exist. So here f of 0 is equal to what? K. We are fine there. Now go to the left hand limit. Go from values which are less than 0. Then what will this become? This will become x by minus x because we are taking values less than x. So plus 2x square, and then see there is a common x here. Otherwise it will go to the indeterminate form. Don't go there. So you can cancel this x and then you will get minus 1 plus 2x. So as x tends to 0, what will this whole thing become? Minus 1. Come to the right hand limit of f at 0. That means what if x comes from the right of 0? That means the values which are greater than 0. Then your modulus x will be what? It will be plus x. So So instead of x put 0, then what do you have? You have 1. So whatever your value of k, it does not matter. Why? Because the limit does not exist. The second condition is not satisfied. The left hand limit is -1, the right hand limit is +1. So whatever you do, you cannot make this function continuous at x. Now with this we come to the end of this session and we go back to where we started. You remember we put up 3 graphs and we said that each one is a different kind of a discontinuity. What does that mean? Look at the first picture. F of a exists. Good news. There you see the f of a. The left hand limit exists. Left hand limit of f exists. The right hand limit of f exists. And they both are equal. That means what? F of a exists. Good news. The second condition is also satisfied. The limit of as x approaches a, f of x also exists. That is also a good news. They are still connected, but these two are not equal. The third condition is not met. So even though the limit exists, even though fa exists, these two are not equal. So you have a discontinuity. Now here what happens? See, the left hand limit exists and f of a also exists. You see here, this is f of a. This point is your a, f of a exists and it is equal to the left limit. But then look what is happening to the right limit. So here also first condition is satisfied. F of a exists. There your f of a is. But then what happens to the left limit and the right limit? They are not same. That means the second condition is not satisfied. The left limit is here, the right limit is here. They are not equal. So the limit itself does not exist. Now look at the third condition. There you have your f of a. So the first condition is all right. F of a exists. But what happens to the second condition? As x comes to a from the values less than a, the function goes to infinity. Here also when x approaches a from values greater than a, here also you see that f goes to infinity. So again the second condition is not satisfied. So this is known as a removable discontinuity, this is known as a jump discontinuity, and this is known as the infinite discontinuity. What did we learn in this class? We saw how to check the continuity of f at one certain point a. We saw how f behaves when x is less than a, when x is equal to a, or x is greater than a. If all those functions coincide, then you have a continuous function. If any of that does not happen, you have one of these cases. So with that we come to the end of this lesson. But then, is this enough? Is it enough to just check if f is continuous at just one point? What happens here or what happens here? What if I want to know how the function f behaves in the whole of the real number line? So I want to know whether it is continuous for every other real number. So how will I do that? That inshallah you will see in the next class. But trust me, we have done all the heavy lifting. All the difficult stuff we have already done. This is, the continuity at one certain point is what requires very comprehensive analysis. We go through all. We go through the indeterminate forms, the piecewise functions and all of that. When that is done, the rest is easy. So inshallah, I will see you in the next class. Till then, you stay safe. Assalamu alaikum.